So we, set out looking for interesting examples. And one of them was like weather modeling, because the weather data is open source. And so given that the data was there, we were like, okay, let's just go try it, right? And that's the beauty of it. Whenever data is available, it's really good news. But a lot of weather scientists did caution us back then. This was back in 21. And they said, no, this is so difficult. There have been decades of development in traditional weather forecasting, and that's very careful, bottom-up physics-based modeling, right? So assuming, this is the fluid dynamics, can you go predict the weather the next day and so on. And so that's how a lot of the thinking was, that AI is just not going to be able to beat the decades of work in weather modeling. But to our surprise, we just went ahead, we trained them, we used neural operators to be able to effectively capture the phenomena. And then we found that it's not only accurate, it's almost as close to what the traditional weather models can do accurately, but also tens of thousands of times faster. So what would take a big supercomputer to run can now be run. And we only needed a consumer grade like GPU. It was a small model, it fit very well, it's very fast, and it's accurate. And I think that just changed everybody's thinking.
Welcome to Latent Space. This is the AI for Science section of Latent Space. I'm Brandon. I work on RNA therapeutics using AI at Atomic AI. I'm joined by my co-host, RJ Haneke, who develops spatial transcriptomics and is the CTO and founder of Mirror-Omics. Today, we're excited to be joined by Anima Anandkumar, the Brin Professor of Mathematics and Computer Science at Caltech. Anima has done all sorts of really cool work combining AI with basically models of the physical world, and has a really diverse background. I don't think I could even remotely cover it. But anyway, I'll let Anima introduce herself. Thank you for coming on the show.
Yeah, thank you, Brandon and RJ. It's a pleasure to be there. And I really like the term latent space, because that very much figures in a lot of my work, because it's really, the world is latent. But yeah, just as a brief introduction, I've been working in AI for more than 2 decades, in a way, before even deep learning, when a lot of the theoretical foundations had to be built for probabilistic models. I worked on them. And then as deep learning started taking off, I also had a foot in industry until recently. So I was at NVIDIA, I led AI research there. And before that at Amazon Web Services, helped found the cloud AI team and build the first cloud AI products back almost a decade ago. So, kind of having this one foot in industry and academia, I think has given me a lot of interesting perspective of how to bring theory and practice together and think of AI at large scale, but also AI that is principled.
A lot of your work has been related to the modeling of physical systems, using certain types of physical systems, which you model with differential equations, and you help model them with using machine learning. So maybe first let's go ahead and talk a little bit about that as a high level, but we'll get to kind of the details about, let's say, neural operators and some of the applications like weather later. But first, I'm actually really curious to hear about TorchLean and how this recent work you've been doing connects with that larger research program.
Mm-hmm. To me, broadly, my thesis is AI and science, how we bring that together, right? So, when I started at Caltech almost a decade ago, that's when, my passion was always science, was physics. But I was doing AI. So how to bring that together was where, the first kind of foundations got laid there. And to me, there are several aspects to that. One is people have been thinking how to use language models for science. Yes, you can do a lot of hypothesis generation. You can have ideas, but ideas are not enough. Right? So you can have a lot of ideas. The bottleneck is going, testing, and verifying that they work in the real world. And so this aspect is where a lot of my recent focus has been on how do we ensure that we can build AI that has guarantees that it will work in the physical world or any aspects in scientific domains. And one way to think about it is, can we model the physical world and keep the physics correct? And that's where neural operators come in. The other aspect is, can we verify symbolically certain aspects? For instance, if we claim that the theorem is correct, we have to go verify that. That's where Lean as a formal language can be useful for verification. So how do we bring that together with language models is where a lot of mathematical reasoning has been at the forefront. And so TorchLean kind of is in that realm where we say, not only that you want to verify mathematical statements, you may want to verify what neural networks themselves claim to deliver. For instance, if you're now using a neural network and you want to ask whether it's going to be robust, say you want to use a neural network in a control loop, you want to control, whether it's a drone, whether it's a nuclear reactor. So all of this, ultimately, when we build AI systems with deep learning into control loops, we want robustness. And so now TorchLean can help us do those verifications seamlessly. So we can now have neural networks be part of the verification loop and have confidence that we can use them appropriately.
We have already discussed on the podcast Lean, and everyone should probably be familiar with neural networks. But neural networks seem very unconstrained. What kinds of proofs are you talking about? Are you talking about bounds on the outputs, inputs? What can you prove with TorchLean?
Yeah, so TorchLean is an overall framework, right? So what it really enables is that you can now write neural networks essentially in Lean. So instead of writing in like PyTorch, it's like a PyTorch-like abstraction, but you can write it in Lean, and so it can be fully formalized in Lean. And then there are several implementations. We have algorithms for certified robustness like Crown. Those are implemented under this framework. So,
sorry, was it like what? Like Crown?
Crown is one of the.
Can you explain about that?
So there are different ways to bound, for certified robustness. How tight those bounds can be. It depends on the relaxation techniques, and sort of without going into those, there's many such algorithms. But we are kind of like implementing them and enabling them in Lean. So we can seamlessly run both, we can both first kind of write down in a Torch-like framework neural networks very simply, right? And then we can also make statements about them formally and verify them. So all of that can be brought together in one framework.
So what's an example of a bound that you could claim? So we're operating a nuclear reactor. We don't want it to melt down. What are the sort of guarantees that you could provide to the inputs and outputs that would help that not melt down?
I mean, the natural one is the certified robustness that I mentioned. So saying that if our inputs are, perturbed by a certain amount, how much is the output going to be perturbed, right? There's sensitivity analysis is another term. And so having those kinds of bounds for different neural architectures, so you kind of automatically get those bounds, can then help us, not only train neural networks to do well in a control loop, but also worry about safety and robustness, stability. These are all part of control systems that people worry about. So that's one example of an application. So it's really more broadly, the idea is you need verification in lots of scenarios that involve neural networks. So control loops are one. Another example is, we used physics-informed neural networks to, say, solve partial differential equations or come up with systems that are guaranteed to satisfy certain physical laws. But we also want to verify, for instance, that our neural network is only trained in finite precision, right? So can we overcome those requirements, and what happens when what are the shortcomings because we are using this finite precision? Can we also bound those?
Oh, right.
So those are other kinds of bounds that work in TorchLean. So all aspects of the effect of precision, the effect of perturbation, all of these, we can we can have algorithms that are implemented in Lean that can be seamlessly now part of the verification loop.
So, and is the descriptive power of the TorchLean, is that sufficient to describe basically any neural network, or are there constraints on that?
Yeah, so it's essentially a PyTorch-like framework, right? So you can just kind of nicely define neural net layers in the same way, but the backend having like Lean helps us formalize and prove it.
And for like transformer architecture, for example, is it reasonable to prove these kinds of bounds on a very large neural network?
So there is the aspect of one is like kind of having the framework, right? The other is scalability. So Lean still has a lot of shortcomings there. It's CPU based, and it's not getting that onto the GPU has a lot of nuances there. So a lot of work needs to be done. So what we've started with is a framework. Making that more efficient, especially at a very large scale, requires still a lot of work to be done.
Yeah.
But that's true broadly for Lean as well.
I'm just trying to understand like how I imagine this. So if I were to take let's say, numerical analysis classes, a graduate level numerical analysis class, you have a differential equation, you have some discretization error or something, and you bound, like, given these properties, I can bound the solution, right? So solving some of these physics-based or AI-based solutions to differential equations, I think historically it's been kind of the Wild West. So I think you mentioned physics-inspired neural networks. Really cool idea. It'd be fun to talk about that a little bit. But I know that sometimes they are particular, and that they don't always work. And I think people don't always know when they will or won't work. I mean, I'm not an expert, but I'm just wondering if that's in your experience. And what I'm wondering is, like, has this helped you understand like the domain of applicability for pins, and is that sort of like the goal, is like you can rigorously say like this solution will converge, or is there not necessarily the same concepts of convergence in a controlled way for neural networks?
Yeah, so like physics-informed neural nets are about like saying that I write down like a PDE, partial differential equations, and hopefully the optimization succeeds and I get the answer, right? And of course, if like optimization was not at all an issue, this would be universal. You solve everything, we're all happy, but that's not the case. And so optimization ends up being usually very difficult, especially for problems that are time dependent, meaning it's not just stationary, you also have time, and the time component in many cases could be turbulent, like in the case of fluid dynamics. You kind of like, if you run it long enough, it can become chaotic. So you really, have like very small fine scale effects matter. And so in those cases, just trying to solve a partial differential equation at all times is just hopeless. Like, this is not an optimization landscape that, I think we can have any handle on. And this is where the idea that from scratch we would be able to solve these equations using a neural net is not possible. So pins don't work everywhere. And our idea of neural operators came as a way to overcome this, right? So saying, we can't rely just on physics constraints alone to come up with answers. We have lots of data available. I'll talk about the weather example where we even collect data, right? So we don't just solve equations and have synthetic data, but we also have real data by observing the weather as one example. So why not make use of all of the data available, so we don't just rely on trying to solve partial differential equations and other physical problems from scratch, because it's really the data-driven approach that makes it possible to get quick answers. And so with neural operators, we can bring both of them together. We can have all the data that's available, we can utilize it, we can add physical constraints, and then that overcomes the limitations that pins face.
Can you give a little bit more intuition on the difference there and why that is possible? So I heard you mention, with pins, you're basically just baking physics constraints into the neural network, but that this becomes unstable over time or other variables. Whereas if you add a little bit of data, like I can kind of intuitively understand why that might help, but can you give a little intuition for what's going on? What's the difference here?
So with the pin, every instance of an equation you solve from scratch, right? At least in the classical sense. So you take the specification of what equation you want to solve, and you hope that the optimization landscape succeeds, which many cases it doesn't. Whereas with neural operators, what we do is we, have lots of data. So we have a training phase. We teach it how to come up with solution for different instances of equation. And so just as in other supervised learning at test time, you can now ask, can you come up with an answer? And you can still have physics constraints as a way to guide that. It can be both data-driven and physics-informed together. But the benefit is because we have data, it's like you're not stuck in an optimization landscape, right? So you know what the answers are during training. So you're now at a better chance to come up with the right answers even at test time.
My understanding is that a neural operator is a function fit to data, or a neural network, learns to fit functions to data. Is that a good intuition here?
Yeah. So, neural operators are in that sense similar to, it's the same as neural networks, right? You're learning on data. But the difference is neural operators you can think of it as a generalization of neural networks. So with standard neural networks, the inputs and outputs are fixed sized. So in language, we have fixed vocabulary, we fix what the input and output are. And same with images in computer vision, in videos, we assume a fixed resolution, and we always, our inputs and outputs are always at that fixed resolution. We can't change it post hoc. Whereas with a lot of this physical data, the idea is our world is inherently multi-scale. So you should not be deciding beforehand what the resolution is. Maybe you have weather data available only at coarse resolution, but really the actual phenomena is happening at a finer scale, right? And maybe you want to, after that, incorporate either additional data at finer resolution or add in physical constraints at finer resolution. So we should be having that flexibility, and we should really think of the world not at these fixed resolution, but one that's happening infinitely, our real world happens at that infinite resolution. And that's what neural operators enable, because they model inputs and outputs as continuous functions that can be infinitely resolved, that can have infinite discretization. And now we can have, at inference time, you can give it now inputs and ask for outputs at any resolution. So you're not just limited to the resolution of training that we see in standard neural networks. And that's what neural operators enable. So neural operators enable us to zoom in and out as we like.
So obviously that, as stated, that any function that's under constrained, right? You could have many, many functions that fit the data. It would be easy to overfit. So how do you regularize that?
Yeah, certainly if you're asking about making predictions at a higher resolution than what's seen, like what we call zero-shot super resolution, you're kind of making some guesses, right? And that's what these models are doing. They're trying to regularize and kind of smoothly extend to higher resolution. But of course, if you now give it the model additional information in terms of, let's say, physical laws. So you could give it partial differential equation constraints, conservation laws, and you can now enforce them at a finer resolution than the data you have. Then there's more guidance in a way. So that way it can now come up with the right answers even at higher resolution, because you're giving it constraints at higher resolution. And so that's how we can ensure that these physics-informed neural operators can work at higher fidelity and higher resolution than even the training data that was available.
My understanding is a lot of your work uses a particular kind of neural operator, a Fourier neural operator. So Fourier is a dual domain. It is extended across the entire domain of the inputs. That's a lot of jargon, maybe. Can you give some intuition for why is that important? How does that help?
What I mentioned, neural operators, as a class of models that allow us to have any resolution input and any resolution output, right? And learns the mapping between them. That's really called an operator. So the mapping between function spaces. So that's the reasoning behind the name neural operator. And Fourier neural operator was one of the early setups or architectures we came up with. And the reason why that's been so successful is because it kind of strikes a nice trade-off between efficiency and expressivity, right? So why is the Fourier space a good one? The Fourier space allows us to, it's a dual space, like you mentioned, but it really allows us to capture non-local phenomena, right? So meaning something that's like non-local in the Fourier domain could be even efficiently captured. And a lot of phenomena like we see in nature, whether it's fluid dynamics, material deformation, quantum chemistry, it's all, there's a lot of them are non-local. The differential equation, like the derivative is local, but the inverse of it is you're kind of doing essentially integration. It's non-local, right? So the solutions are non-local. And these models are able to capture that. But at the same time, doing Fourier transform is efficient. And it kind of like nicely captures a lot of inductive bias we see in many of these natural phenomena. But this doesn't mean that we are capturing the world entirely in the Fourier basis, right? It's not a linear representation in the Fourier basis, which is what classical numerical methods do. We add nonlinearity just as in transformer and other neural nets in between Fourier layers. And we also add residual collections. So all of these architectural aspects that are inspired by other neural nets that work well in other neural nets, bringing that together really kind of helps us get best of both the worlds. So you can think of like, if we were to use transformers and we require a very high resolution, it would become untenable because of the quadratic complexity and all-to-all connections. On the other hand, if you did that with Fourier transforms, we have like quasi-linear complexity, and still we have global connections. In a way, we can model these non-local phenomena. And so that's why it's a nice middle ground.
So that allows you to learn from what is happening on the other, like it's talking whether like what's happening in Chicago may have some impact on what's happening in San Francisco. Or maybe not, but that's the idea.
Yeah, so that's the idea in time, like kind of, yes, at this point may be local, but eventually they have an impact in other locations. And so both in space and time, we want to capture that dependence.
Yeah, so what happens today in Chicago will have an impact in a month in San Francisco or something like that.
So there is like both the short-term and the long-term effects. So in a short-term, like we think about predictable weather, but longer term, we're talking about climate, right? So what happens, you may not be able to say precisely, what happens in Chicago, what will happen in San Francisco. That's like the butterfly effect. On the other hand, we can kind of give averages. If there's heat wave in this kind of overall region, we kind of have an idea that it's going to be higher than average temperatures. So those are the aspects we can capture together.
From an architectural standpoint for all the AI engineers here, are we just talking about doing all the work in the Fourier domain, but it's basically the same neural network, but I'm just operating in the Fourier domain? Or is there other aspects that are required in order to do this properly?
So think of it, I guess maybe the easiest way to think about it is, if you think of a transformer architecture instead of like the attention map, you now have the Fourier, but you still have other nonlinearities. You have like, the residual, you have, many other parts of the architecture still there that give it like expressivity. And we have lifting to higher dimension, like, in a channel space to give it more expressivity. So all of those kind of best principles are still available. But the Fourier helps us capture that all-to-all dependence without requiring very huge complexity that we see in transformers.
That makes sense.
The other advantage is that it gives you the natural multi-scale with sort of a implicit cutoff is, the sort of, if you have a signals background or physics background, you might ask, in linear, if you're doing everything linearly, there's a maximum frequency and, above that, you can't represent anything. But how does adding these other architectural changes in a nonlinear domain actually affect, your choice of frequency bounds?
That's a great question. And that's where the expressivity comes in, right? Mm-hmm. Otherwise, if you're just taking a Fourier transform of a signal and trying to represent it, that's what numerical methods have also attempted to do. And that requires very fine discretization. And that's why it's very expensive to do the simulations in a classical way. And instead, if you want to move away from that and say we want to learn the features, which is what deep learning is all about, then we cannot force it to be only in the Fourier domain. We have to give it nonlinearity to figure out what the right basis for, the best basis to represent the signals are. And so that's the kind of nice kind of combination we have, that it's like all these nonlinearities will help it kind of, find the right latent space. No pun intended.
This is the right latent space.
It is the right. And so, and if you do Fourier in that latent space, that may be a more efficient way to represent. So that's one way of thinking, because, first of all, we're lifting the signal to more dimensions. Even if the signal is 2 or 3 dimensions, we are now lifting it to much higher dimension. So in that space, the idea is it's easier to learn. And we're doing it as a nonlinear lifting, right? So there's already a latent space there. And then we are doing further nonlinear transformations in between our Fourier transforms. So that means we are saying, yes, maybe with these limited number of frequency modes, it's not expressive enough. But when I add nonlinearities, I can kind of more nicely capture them.
Yeah. So you started your career back before neural networks were, I guess, taken off, right? So I think back then people really did think a lot about, appropriate basis sets and, function expansions and orthogonal polynomials or whatever. How does that evolution from, your research standpoint, as the community has evolved from that to, just screw it, throw it all in, it seems like you still believe in at least some of those concepts as being guiding principles. Do you think that there is actually still lessons to be taken from, classical mathematical, rigorous mathematical techniques, that you can use those techniques to actually help improve modeling of the real world, even if you still are just throwing the kitchen sink at things?
No, I think it's a nice, I think there's a trade-off involved. I mean, it's funny, my undergraduate thesis more than 2 decades ago now was on fractional Fourier transform, right? So, and so, yes, I mean, by themselves, that wasn't enough to do computer vision, but I was curious, okay, what are these techniques and how well do they work? And so, I'm completely with you that we cannot just force ourselves to use Stone Age techniques or classical techniques, right? I mean, so we have to have feature learning, we have to have flexibility, expressivity, they have to be easily optimized. So all of these aspects are very important with deep learning. But when it comes to the physical world and physical data, it's never going to be as plentiful as we see with language models, because we are, our weather model had about 50,000 samples, right? 50,000 samples of fairly high resolution, global weather maps, but it's nothing like what we see with language. And in other domains, it's even less because it's so expensive to simulate and the real data may just not be available. And so here we have to think about the inductive biases more. We have to add in the physics constraints. It cannot be just reliant on data. And that's where I think a little bit more thinking of the architectural design comes up. The other aspect is computational complexity. So think about language. It's just one dimension. And even there, the context length, we are getting to millions and we are struggling, right? I mean, on the other hand, now we are thinking about not just 2D, 3D, even 4D, 3D and time. And if each of the dimension is even a few hundred grid points, which is where, industrial scale starts at like 1,000 grid points in each dimension, we're talking like hundreds of billions to even a trillion context length, right? So forget ever having a transformer for anything of this scale. All of the world's compute will not be enough. And first of all, they all have to be co-located to be able to ever do this. So that's why we need other architectures.
But I would push back a little bit, right? We have the vision and video language models, right? And they basically learn a mapping.
But the resolution is very low. Mm-hmm. That's the key. Like for the physical world, the resolution, what we require, I mentioned like 1,000 by 1,000 by 1,000 by 1,000. So there, if you count that, that's like already in hundreds of billions.
Yeah.
So we are not doing that high resolution when we think about images and videos currently.
I have a friend who...
And the video is also like autoregressive. So it's essentially only like you only need to do the next step.
Right, yeah. But you're learning, generally you're learning a code book, right? So you're kind of learning the bias of the latent space or the real world to the latent space. And so that if there is a compression that you can do from the physical world into the latent space, then these autoregressive techniques have been successful.
Yeah, but the idea is, a lot of these autoregressive and techniques for vision and video models are for mostly looking good, right? So they are not for very precise simulations, and they're having that higher resolution and details is really important. And so we need to at least take in the data of that high resolution, right? So we need to be able to process that and reason over them. And so this is where a lot of the bottleneck is, because we cannot afford to just throw away everything and say, let's just have 100 grid points in each dimension or 50 grid points, because there just isn't enough detail to correctly model phenomena like fluid dynamics, plasma, how materials deform. So all of this requires high fidelity. And for that, we need high resolution.
My understanding, you have a thesis that AI needs, to incorporate the physical world into it in order to scale and be accurate going forward. Many people have this thesis. You are somewhat unique in that you have several examples of applying neural operators to the physical world in this way. And then it seems like you're constructing a thesis around your experience here. So can you share with us some of the really interesting and exciting looking things that you've done using neural operators and other techniques?
Mm-hmm. Yeah, for us, when we started with neural operators for partial differential equations, but also more broadly, you don't even need to assume they're partial differential equations, right? It could be any spatiotemporal or data at multiple scales. So we, set out looking for interesting examples. And one of them was weather modeling, because the weather data is open source. It's available called the ERA5 from the ECMWF, the European Agency for Global Weather Modeling. And so given that the data was there, we were okay, let's just go try it, right? And that's the beauty of it. Whenever data is available, it's really good news. But a lot of weather scientists did caution us back then. This was back in 21. And they said, no, this is so difficult. There have been decades of development in traditional weather forecasting, and that's very careful bottom-up physics-based modeling, right? So assuming, this is the fluid dynamics, can you go predict the weather the next day and so on? And so that's how a lot of the thinking was, that AI is just not going to be able to beat the decades of work in weather modeling. But to our surprise, we just went ahead, we trained them, we used neural operators to be able to effectively capture the phenomena. And then now to our surprise, we found that it's not only accurate, it's almost as close to the what the traditional weather models can do accurately, but also tens of thousands of times faster. So what would take a big supercomputer to run can now be run. And we only needed a consumer grade like GPU. Like, it was a small model. It fit very well. It's very fast and it's accurate. And I think that just changed everybody's thinking. After that DeepMind, Huawei, many others followed us a year later, released their own models. We were the first to actually open source our weather model, FourCastNet, and do it permissively. So that's what allowed companies, weather agencies, everybody to build on us. And so, it's been a really interesting revolution to see that the weather models are now out there. Weather agencies are adopting them. And it allows us to now have small weather agencies in the global south, for instance, have the same kind of fidelity that very big agencies were in the past only able to do, right? So it's democratizing weather modeling. And so that's just one example of where there's been very quick, rapid progress and a paradigm shift in terms of saying that, now we can have AI as a reliable way to do weather modeling.
I saw that, the models that you mentioned, you made an insight that nobody else had, and that people were able to devise other mechanisms to kind of follow behind you. But there was some sort of shift in thinking that was required here. And was it simply we believe that there's enough structure in this data to learn, and that people are just doing it wrong, and people found other ways to learn the structure, but that your method was very
So let me clarify, right? So there is, first of all, the very first work was to just say that, look, traditionally this has been done with trying to solve partial differential equations, each time doing it again and again. Whereas AI learns from data, learns patterns, and can be just as accurate but fast.
Yeah.
And then the next iterations was to say, how do we make it even more accurate? And there's the aspect that, there is the short-term weather, like what is predictable for the next 2 weeks. And then there's the long-term, going to subseasonal to ultimately climate modeling. And traditionally, what people did was to have different models for these different scenarios. So there's a different kind of system that works for short-term, another system works for long-term. But to me, there's only one Earth. If you want a foundation model, if the claim is that it should be able to do both very short-term as well as very long-term together. And that's where in FourCastNet 3, the latest iteration of the model, we're able to do both. And that's because you also incorporate the spherical geometry of the Earth. And so with a lot of the other architectures that have been getting fairly good accuracies for the short-term weather, when you run them for longer term, when you run them for like several months to even year, even before that, it just very quickly blows up, right? Because it assumes the world is a rectangle, which it isn't. And so incorporating all of the geometry and that information into neural operators means that we can faithfully run the same model also longer term and make this into a climate model. This is where the Allen AI Institute has now built climate models based on our neural operator architecture. And that's the only one that works as an AI emulator, right? None of the other architectures work for climate because climate requires us to assume the world is a globe, and that if you are repeatedly rolling out, you kind of keep that information. Whereas if it's like a narrow surrogate, that's what I consider a weather model. You just narrowly look at a few metrics. Many different architectures should do the job, right? But if you are asking one architecture do a range of different tasks like a foundation model, that's where incorporating the geometry of the Earth, which is that it's a sphere, and using neural operators an efficient way to do that enables us to accomplish that.
Yeah. So FourCastNet, you said trained on 50,000 data points. Can we just talk about what does this look like? Like, what does the data input look like? What are you actually trying to predict from here? And then what is sort of the large scale? You said you're going from weather to climate. What does it look like to do that generalization? Because I could imagine if you have 50,000 data points, these are, some high resolution in North America. then they might even depend on the local geography. Like if you are always modeling Kansas, is this going to transfer to let's say the Swiss Alps or something, and then does that transfer to the Himalayas?
So first of all, to clarify, we are training it on the global weather model, right? So we have all the information around the Earth, and then we are, asking it to predict, like, given the current weather, like say wind conditions, humidity, and so on, what happens, in an autoregressive way, and it's every 6 hours. So what happens in the next 6 hours, and so on, and you roll out and you train the model to predict. And so, you can have potentially the same model predict forever, right? So, but the predictability window is like the weather. And if you want to go beyond, you have to do what we call ensembles, meaning you have like a probabilistic estimate of what happens in several months to years. And that's how you get a climate model.
Okay. So you actually have an ensemble of these local predictors, and then you use some sort of statistics on the ensemble to get a climate prediction.
Yeah, so you kind of like have several rollouts. Essentially, you have several trajectories of rollouts, and then you get
efficiency is actually pretty key here.
Yes, and that's the biggest bottleneck with traditional climate modeling, that it's so expensive to do even one single run. You have to do long trajectories, very, very high resolution. And, that's why we don't have a lot of very high resolution ability to do climate change predictions, for instance.
So how do you validate climate? So you do lots of rollouts and you look at sort of how things evolve kind of in aggregate. I mean, Nisi said butterfly effect. Locally, I think we can believe even a perfect climate model or perfect weather model would only give you maybe 2 weeks before it becomes non-computable. So you do lots of rollouts. There's some chaos. You average all these things. How do you actually validate that this works over long enough timescales?
Yeah, and it's a tricky question, right? So for instance, you have to kind of ensure that you satisfy all of the physical constraints. And if you just do a standard rollout, that is likely not going to happen. And so some of the ongoing research we're doing is how do you kind of enforce the right physical constraints as you do the rollouts. Like you don't want to completely wash out the fine details, because then it's not accurate. But on the other hand, if you keep them, you maybe physically they're invalid. So this is still an open problem. And that's what makes it difficult, that you want AI to be fast and you want to be able to do these long climate simulations and at the same time be able to have full confidence in them. But these are things we are working on now.
I don't know if this falls into weather or climate, but we recently just had one of the most extreme heat waves in the history of modern climate data, right? Just right here in the kind of Southwest United States. I'm wondering, I don't know if you were involved in this regularly, but do you know if you or anyone actually modeled that or predicted that correctly?
Yeah. So we have, I don't have information on this specific one, but we've tested in our latest FourCastNet 3 model extreme weather events of all kinds, right? And that's the key, that's where you need probabilistic answers. So having just one deterministic output and saying that this is the weather is not enough when we are looking at extreme events. So we need careful probabilistic calibration, and we show that we are able to capture those well. And I think that was the surprise, even in our very first attempt, that we visualized certain hurricanes and storms, and it was able to do well, which is very surprising, because you would think that rare events are not something AI would do well, right? It would do well on typical events. But I think this is where, more broadly, the lesson is the physical world may be more forgiving, because, where there are extreme events like hurricanes that have very specific physical signature, right? So it's like extreme, but in a very specific way. So maybe you don't need as many samples because the physical world has a lot of structure. And that's something we see this again and again, that there is a lot of structure in so many other examples. I talk about plasma and fusion reactor. We barely have a few thousand samples, but we are able to accurately predict events like disruption very well. And we are able to do that 1 million times faster than what traditional simulations were able to do. To me, yes, all these sound very surprising, but it's because I think the nature helps us a lot. It has a lot of latent space structure that I don't think traditional numerical methods are able to uncover, because they are focusing more on correctness, that in any scenario, you should be able to solve these equations. On the other hand, with AI, it's learning from data, it's uncovering the structure, it's uncovering how easy or kind of tractable these problems are, and that's what we are seeing in many cases.
Yeah, I've had a similar analogy. So from, my own domain is probably closer to computational biology, but, AlphaFold is the obvious, really exciting development in the community. So the solving protein structure prediction, and of course, all the caveats of what was actually solved. So I think we discussed this in a previous episode with the Boltz team. Encourage listeners to listen to that if they want more. But one of the, I think, key points about protein structure is that it really is constrained by physics. And that's why it was, in some sense, one of the few big wins in the field of biology, which is otherwise very complex. And we've had trouble, generally speaking, making a lot of success. And it seems like problems which are solved by differential equations, or I'd say modeled well by differential equations, have a lot more room for also integrating these techniques as a general form. I don't think there was a question there.
Yeah, absolutely.
Editorializing.
So getting back to my question, we have climate, or weather and climate. We have plasma. We have biology. And I know that you prepared for us a few visualizations.
Oh, yeah.
Can you just share with us what does that look like? What are the visualizations, and then what is the thread that runs through here? And I think maybe the listeners will already have a hint about that, but I'd be really excited to see that.
Yeah, I can certainly share some of them. This one is just kind of showing that we have world at different scales, right? And these are examples of phenomena happening at different scales, from atomic to protein to even planetary scales, like the weather we talked about. And, we need to capture all of that. That's what neural operators are designed to do, and to can, feed in data at these different scales. And that's really like the aspect that makes a lot of the physical world problems hard, that need for fine scale. We talked about how a lot of traditional computer vision video models are just designed to make things look visually good. And that requires low enough resolution, it's tractable, autoregressive, it's enough that, it works out, it's short enough videos. But that's not how a lot of the physical simulation for industrial scale, high fidelity work. You really need high resolution. The atmosphere is one example. Like depending on the resolution you observe, different phenomena can be captured. So you just miss that out if you don't have that high resolution. And now the question is, with AI, can we do this much faster than what we could with traditional simulation? And this one with neural operators is kind of showing that, if you used a standard neural network and you had a fixed number of pixels like you're seeing on this side, and you zoom in, it gets blurry, right? That's the end of it. There's nothing beyond those fixed resolution that you can capture. But the idea is, with neural operators, because it's a function space representation, meaning you can keep zooming in, you can add the relevant details either by giving it data at higher resolution or physical constraints at higher resolution. You can kind of bring that multi-scale phenomena together.
So where are the physical constraints? I assume physical constraints here are like local simulating, fluid equations or some sort of hydrodynamic?
Could be, right? So it could be of any nature. The idea is now you can add like conservation laws, for instance, in an incompressible fluid. You can add like material deformation, like how things stretch. So, or it can be a full partial differential equation. So that's also an interesting question. We've been researching how is the curriculum of different physics. Like you mentioned, some physics may be very hard to impose or add as a loss function. Others may be easier. So you also need to kind of think about what to impose.
And the intuition is that when I'm adding a physical constraint, I'm adding it to the loss function. Is that more or less what's happening?
Yeah, because that's what is tractable. Making it a hard constraint is not tractable, whereas adding it as a loss function. And of course, there's still the balancing of that loss with the data we have. So we have to, do that in the appropriate way.
Right.
Yeah, so as I mentioned, this is the example of the weather model where here we are showing how we are able to capture like atmospheric rivers, which is the phenomena we see here in California, resulting in light storms. I think we have one expected later this week. So
we'll hold you to that.
So the idea of why I showed this is this kind of global phenomena, right? These are like thousands of miles wide. So you really need non-local models that capture these very large span phenomena and do that accurately. And that's what our neural operators are able to do.
So the training data for this is, you were talking about this a bit before, but I'm still wondering, what is this? This is weather satellites, or is there ground-based data? Is it some hybrid of the two?
It's kind of a combination of different sources. So it's what we call reanalysis data. So this is historical weather data that is in a way reanalyzed, meaning that the raw satellite data is combined with essentially what the physics solvers tell you together, assimilated. And so this is made available by the weather agencies, and we can train on them.
So you're saying that they take a low-resolution data set, which is compiling all of the world's data set, all of our meteorological data we have across the world, and then they do short-time simulations using physics-based, classical techniques to fill in the details.
Yes.
And you can do that over short time spans, but as you go farther, it breaks down very quickly.
So you're amortizing that across everyone would have to do that. And so somebody does it, and then you are able to take advantage.
Yeah, I mean, this is data, right, that's already prepared. But the idea is already this data assimilation with physics kind of makes our model physics informed implicitly. So it's able to kind of, keep that information, and that's why maybe that's one reason maybe it does well on even extreme weather events. Yeah, so this is just showing that our model is available in ECMWF, which is the weather agency, the European Weather Agency. And so this was launched more than 2 years ago, but, I think fall 2023. So, I think ECMWF making these AI-based weather models available to the public, to me, was a very big step, because that's where everybody could see what's happening. There were several hurricanes, for instance, there was Hurricane Lee, and that's where the public could see what are these weather models doing. For instance, our FourCastNet was able to correctly predict that the hurricane making the landfall several days earlier compared to the standard weather forecasting models. And so the idea that these models could be very good for extreme weather events and do early prediction, both for human lives, for economic costs, is a very big deal. And so that's when the public kind of got a lot more, I think, buy-in and from weather scientists because of how well it was doing in these events. And this is what I was talking about in an ensemble prediction, both for extreme weather or if you're thinking about climate. It's not just about looking at one trajectory, right? Because, unless you're somebody with a Sharpie somehow saying where the hurricane is going to go, no pun intended. But what you really want is the probabilistic prediction, meaning, I'm going to try adding noise levels to my initial condition. When the hurricane is forming in the Caribbean, I'm going to add some noise because anyway it's noisy. I don't know truly what the measurement there is. And then I'm going to look at what happens to the possible hurricane tracks. And then I can come up with a probability of landfall in different regions. And that's how I can do risk assessment. And so this is where it gets even more expensive for traditional weather models, because you have to run all of these ensembles. And now AI weather models being so fast, tens of thousands of times faster, means we can now do very large ensembles. And this is a very big improvement in terms of what we can do for risk assessment.
Have you gone through and done, let's say, looked over the historical hurricane maps and then tried to do ensemble predictions and calibrated how often your predictions are, like a code?
Yeah. So in FourCastNet 3 paper, there are, we have metrics of like extreme weather events and ensemble prediction. And in fact, we've trained the model to do good ensemble prediction. And so this is where the calibration matters for these kind of events.
What was the sort of key insights or developments in FourCastNet 3 and versus 2 versus the first version?
Yeah, so the first version was kind of the using like the Fourier neural operators, but we didn't incorporate the spherical geometry, right? In this next version, we said, I think, it's important that the world is a sphere because, first of all, otherwise it's distorted. So you kind of are not predicting
dumb question, but if it wasn't spherical, what did you do? Like a Mercator projection or something?
Yeah, the standard, like kind of the, like as you, all the other weather models do the same,
really?
Right?
Okay.
So they just kind of have the standard projection and then, predict the weather, and which is okay for short-term prediction. But when our goal was to have the same model also do longer term, and that's when incorporating the spherical geometry added this additional stability. We could do longer rollouts. And then in FourCastNet 3, the idea was it's not just about deterministic prediction. We want to get ensemble predictions right. So we have to train them based on this objective, that we get the probabilistic predictions correct as well.
How long are you predicting out, and how many rollouts are you doing?
Yeah, so the rollout is how long you predict, right? So each step is 6 hours, and then you predict for however long you want. You just have to roll out.
Sorry, how many examples in the ensemble do you have?
So, and again, that's our choice. We can have like ensembles of different levels. So I think it's like a few tens or something, like is what we are currently, shown, but you can do much larger too.
And that's adequate to get out how far? My intuition is the longer you want to predict, the more.
So not necessarily.
Okay.
It's really like about, again, calibrating the ensembles and ensuring that they have the right spread rather than, So,
okay, so you have tens of these models or examples in your ensemble, and that even with a very, very long rollout, that's adequate.
So again, there's, as I said, a lot of still outstanding questions to do very, very long rollouts, right? Because you do need to incorporate the physical constraints in a way to ensure that. That's something that we are actively researching now. But these models that we have are able to do the longest rollouts compared to any of the other weather models that completely ignore spherical assumption and a range of other things.
So when you say incorporate physical laws for climate over long times, I mean, what does that look like? Because there's a lot of local conservation, which may be just broken if you take an ensemble average, even though any given snapshot respects that.
No, the idea is to make sure you look at each ensemble member and it respecting the physics.
Okay. You're not assuming the ensemble, you're not deriving a coarse-grained equivalent of a probability or something.
Because then you would lose that, resolution and the fidelity.
Okay.
That's a little confusing to me. Wait, so it's not an average. Well, how are you combining the ensemble?
No, you are doing the average, but you're predicting each one.
Oh, you're predicting each one separately. Yeah. Okay, yeah.
So each one independently satisfies these constraints, but the ensemble, it does not. Yeah.
And so that's how you ensure physical validity.
Okay.
Yeah.
So when you go on a sphere, you operate do you use basically spherical harmonics or some sort of?
Yes.
Okay, yeah. You have a
Yeah.
spherical basis for it,
Exactly.
which is actually very natural with Fourier network. It's probably
Exactly.
much harsher if you're doing other. Yeah.
Exactly. So that's where the, the Fourier saves us.
Yeah. Yeah.
Can incorporate these geometries well. And so I think be very faithful to, what the globe is.
Yeah, arguably it's much more natural than like a Mercator projection or whatever other.
Yeah, which is like Greenland becomes huge. So that is a different story. But I think that this is where I think the aspect of more broadly incorporating more of geometry and information about the domain becomes a lot more important for the physical world, right? So this is me again emphasizing that we need to incorporate more of the structures, because one is the data is limited, and the other is a lot of what we are asking is extrapolation, to go beyond than what it's trained on. We're just training it to predict the next 6 hours and maybe do a little bit of multi-step fine-tuning for autoregressive rollouts, right? So we're not training it to do very long, like a climate simulation, because that's just too expensive. But we hope magically it works well. And it cannot if you just say, I'm just going to put a standard transformer or whatever else there, and it won't work out. So we added more of the domain constraints like spherical geometry. We add in maybe more of the physics in certain ways. And that's where it becomes more interesting algorithmically as well. There's more involved design here.
So the time scale that you train on, how long is that?
To predict for the next 6 hours.
Oh, so only 6 hours?
Yeah, and a little bit of
That's
multi-step fine-tuning.
I see. I said that. Okay, understood.
So which is very surprising.
Yeah,
right?
that is very surprising. I would have expected it was weeks or months.
Yeah,
whatever.
no, and then it kind of just works well, even for like now we are showing for several months that it's able to do that.
The number of steps is on the
hundreds or thousands.
and that your Fourier basis, it's many times the sort of base harmonic.
I mean, this is like that's in space, right? So we're talking rollout is autoregressive in time.
No, but like in time, maybe I'm misunderstanding here, because it's in Fourier domain, right?
No, in time it's not. That's what I'm saying. It's autoregressive.
I understand. Okay.
So in space it is.
Yeah. Interesting.
Yeah.
Okay.
What's the angular resolution?
At least in this scenario. In other cases, we also have time is also represented in the Fourier domain, and that's a question as well. Can we do that? But in this example, it's autoregressive.
Got it.
Yeah.
What's the angular resolution that you use for this in the spherical version?
Yeah, so it's so all of the data that's available is like I think a quarter, like 0.25 degrees. So
in terms of L, maybe, or in terms of like a spherical harmonic frequency,
so this is like you mean like how many modes we utilize? I think so for that resolution, we essentially utilize, I think most of it, only a few of them will live out. I forget the details, but
I'm just curious, like, what is the actual angular resolution on the globe that you are resolving to, or maybe just the physical resolution?
Yeah, and that's what because that's the data we get, right? So right now the data we get is like a quarter, like 0.25 degrees.
Totally. Oh, okay, like a 0.25 solid angle.
I think kind of comes out to like 700 by few thousand like resolution. So, but this is already standard like kind of process.
Yeah. And just trying to understand, like, how large is the basis do you need to represent that?
Yeah, that's really depends on the resolution. And the idea is, right now our weather data is just limited by this resolution. But if you could, you could like kind of do synthetic climate simulations of even higher resolution, right? And that's kind of the next thing on how to combine these together.
Do you think you can predict with super resolution, basically resolution lower than the data provided?
Again, like, yes, we can always predict them with the neural operators, but you do want to incorporate more of the physical constraints to ensure that they are valid.
Okay, so can we talk about some of the other
yes, I know.
technologies?
There's a lot. So this is just showing like how, what I described, that on the left, where the world is being assumed it's a rectangle, it blows up very quickly. And on the right, because we assumed the world was a sphere, it kept rolling it out and it kept being stable. So
I still see a little bit of a singularity there.
yes.
Is that right?
And it's still like, so the idea is, yes, because it's a very long rollout and we have no guardrails of physics, we are not, kind of projecting it to the right physics, right? This is full extrapolation. But the idea is the sphere assumption stabilizes it to a much greater extent.
Compared to the left, it's much better.
Yeah.
But if you're in the South Pole, you're still not going to get a good
Exactly.
forecast.
So it's the poles are the hard part. So this is the example of the fusion reactor. So this is a tokamak, and we are able to model the complex plasma evolution and do this 1 million times faster than what we could do with traditional simulations. And this was, in a way, we're creating a digital twin of the plasma, right? And then we can, do further things. Like right now we are, as a next step, looking at like control, but with a full valid physics, like being able to prevent disruptions ideally and make fusion sustainable.
So are you simulating MHD equations here, or magneto hydrodynamics equations?
Yes.
Okay, yeah. And then so for context, disruption in this case is this phenomenon which plagues plasma physicists, where at some point your entire plasma collects in a little tiny beam and then shoots a strong, right to your containment vessel and blows it up.
And it can damage the reactor. And that's a big bottleneck, because then you have to kind of shut it down before that happens. And then plus it's no longer possible to have a sustainable fusion. So there's a lot of open challenges here, but the idea is, it's very expensive to go to physical experiments. The more you can capture that in the digital twin but ensure physical validity, the more you can even do design and other considerations in the digital realm. We can hopefully make advances, and these are the first steps towards that.
The goal is that if you have one of these events, that you can somehow adjust the magnetic field so that it contains that and stabilizes.
Yes, and that's the next step we're doing now. We are looking at like designing both the control and the simulation together.
Are you working with a specific lab? I'm just curious.
So this one was with the UK Atomic Energy Agency.
Okay.
And now we're also working with a few others here in the US as well. So we're, kind of getting the information from many different approaches of fusion itself. So this is the tokamak. We're also working with stellarators. We're working with different
The stellarators are tricky.
Yes. But the idea is ideally, like our goal is to be able to design them in the digital twin. So can we come up with good designs that would make it maybe more practical? And so that's, I think, also a good thing as an AI person. I'm much more like, agnostic and not picking a winner beforehand, right? Like I like to work with different approaches, and see whether AI can accelerate all of them. And then we can kind of, not prematurely rule out one approach over the other. So that's what AI enables us to be more kind of taking risks and exploring different approaches, as opposed to in the physical world, trying to build any of these. You kind of have to cut a lot of the risky ones and say, I'm only going to do this because this is the most likely to work.
I noticed over your career, you started out spending a lot of time on, really theoretical foundations of mathematics of machine learning. And maybe, I don't know, something like 6-8 years ago, you started working a lot on applications and branching out in a diverse set of problems. What sort of prompted that shift in your approach and what you're looking at? I mean, you're still working on very hard math problems as well, like, for example, the TorchLean work. But the applications have really grown, and I'm wondering what prompted that, and what were some of the lessons you've learned since then? Yeah.
Sure. I mean, to me, it's like, I feel like I've grown along with AI, right? So when AI was in this where neural nets were not working because there wasn't enough data and all kinds of other reasons, then you kind of have to build the theoretical foundations and try to hope that leads you to a place where, you get algorithms to work, right? And back then, like tensor methods was with that idea that pre-deep learning, we still wanted structure. We have probabilistic models like latent Dirichlet allocation for topic modeling, and solving those were hard, but now tensor methods gave us a way to be very practical. It's parallel and can be done at large scale, but still has nice theoretical basis. So that was where, was starting off. And then as deep learning started taking off and we could see that it works well in practice. And yes, there is a little bit of maybe theoretical understanding, but not a whole lot because of the way how complex it is. To me, theory should not be a constraint, right? It should be an enabler. And so that's where a lot of the exploration was of to make this work well in practice, and into Amazon Web Services, then NVIDIA. So really making things work at scale and really kind of getting hands dirty, right, was kind of where a lot of the development is. And now I see a full circle because a lot of purely data-driven approaches, in a way, seeing saturation, right? So now we want to ask, okay, either make them more hardware efficient, right? There's a lot of now room to kind of say, can we now, make them much more energy efficient or hardware efficient? So that's one aspect. But the other is areas like this, where in the physical world, we don't have enough data. We are asking for hard extrapolation. We want to think of doing discovery. By nature, it's about extrapolation. So we will never have data about a new discovery, right? That's by definition. And so there we need to, again, go back to thinking in principled ways, whether it's architecture design, algorithm design, the right loss functions. So we need to be much more mindful. So I see that coming a full circle, because all of the things that work with deep learning, let's take them, but make them a bit more principled.
There's several other applications which seem very natural. I'm wondering if you've worked on these, or did I just miss some papers? If I did, I'm sorry. So some examples are design of electromagnetic circuits, I think is a big one, or maybe not a big one, but I think will be coming up in the near future. Design of, let's say, materials, design of, let's say, dissipation in heat sinks, or any sort of fluid flow. I guess I'm going through what differential equations do I know? Electromagnetism, I know diffusion equations, MHD, yeah. I'm wondering some of the other domains that are
to me there is just endless possibility, right? So there as you can just have this work on any data, and we have several other examples. So this was being able to ask, can we sequester carbon dioxide underground and model how carbon dioxide expands, or what is the pressure buildup in these reservoirs, and can we kind of model how they migrate over several decades. And so this one we were able to do much faster than what traditional simulations can do. The other aspect is being able to do all kinds of geometric shapes, being able to model aerodynamics in cars, planes, and so on. And so again, this is a nice example of a latent space, because you can transform a car or any other shape to a donut, and then model on the donut, and then transform the donut back to the car.
You didn't turn it into a coffee cup. Is that the classic joke? Your donut in your coffee cup.
Exactly. So the idea of a latent space to handle all kinds of different geometries and be able to capture the physics there in the latent space well means we can now have a model that generalizes across a lot of different geometries.
Am I understanding that maybe the larger vision here is that you can train a foundation model in the sense of being able to model many different physical phenomena with the same model. And so you may fine tune, or there may be some kind of prompt that you give it to have it understand the particular geometry, but that you sort of on all these different physical problems you train, and then you have your particular one, and you're able to model that very effectively.
Yeah, that's really the future, right? Because we have foundation models for language, maybe vision, but not for physics. So, the idea is, instead of right now what we've seen are narrow surrogates, and we're trying to broaden their scope more and more, but ideally we have much broader models that can work on a range of phenomena, but also multi-physics. So not just have like one single physics, but coupled physics. The real world has all of the physics kind of coming together in coupled ways. So can we bring all that together? So that's one aspect, like, have foundation models that can do design, that can do simulation. But the other aspect that's really interesting is the inverse problem, right? So can I now not just simulate, but ask what is the best design? And then these kinds of models can do simulation, but you can even do that implicitly and come up with the best design, rather than in the earlier era of it was humans trying to come up with design, then you go and try to simulate or go to the wind tunnel, whatever physical testing, and validate that. But now you have AI come up with optimized designs, but you have the guardrails of physics. So you have models that are accurate in physics, you have the confidence they work well. So you're kind of able to do that as well in the same model.
Is there a reason, have you seen any evidence that you talked about these sort of multi-physics being able to transfer, or that you may be able to generalize to sort of unseen physics?
Mm-hmm. So, the physics by nature, if it's completely unseen, it's not possible to transfer, right?
Sure.
If you're saying that we're going beyond the standard model, there's absolutely no data. That's not possible. But if you're asking about, for instance, there is the, say, I've shown it examples of just how the heat propagates, and the other examples of how the material stretches. And now there's coupling, because of heat, there's also stretching or kind of the joint phenomena. You could now hope to fine tune with much fewer samples because it kind of individually knows this phenomena. Then combining them together, maybe it can't do it from scratch because that's still too much to ask. It's highly nonlinear and coupled, but it can do it with fewer examples. And we've seen evidence of that in a lot of our papers, that you're able to kind of essentially build up a curriculum. And that's what we see again and again in many of these examples, that, the real world, we can kind of control a lot of curriculum and say, let's kind of build in modules and put them together. And that's what it now allows us to do in a systematic way here. I guess the design aspect, I don't know if we wanted to show very quickly. So this one was looking at designing the mask for inverse lithography, meaning now this is an inverse design problem. And we are also able to do that for designing gates in quantum dots. This is nonlinear photonics. And all of this, what is common is the idea that there's a forward model that is simulating the physics, but now what we want is the inverse design, the problem that we can optimize the best design. And humans are usually not good at this, right? We are not good at looking at highly nonlinear phenomena and say, somehow maybe this combination of all these gates coming together helps pull the electrons together in a quantum gate. And so our collaborators were struggling to do that manually. And with AI, we're now able to come up with very efficient designs, but also those we know actually work because we have already the simulation as part of the loop saying that they work well. So I think these are examples where we see that it's not just about simulation, it's about really novel designs and novel discoveries that enable us to move the needle of innovation itself.
Each one of these examples takes a lot of domain knowledge. How could somebody take your basic research, if a domain expert, and quickly get started applying neural operators and the other frameworks that you've developed to their problem?
Yeah. Neural operators are an open source library. It's extensively already adopted. It's part of the PyTorch ecosystem. It's, used by a number of not only researchers, but also in companies. We have a lot of documentation there. So I encourage people to go there. We have many different architectures, examples, recipes. So I think that's a great place to get started.
You recently joined the UN Scientific Advisory Board. I know we're running out of time, but maybe just Can you quickly give a bit of the story behind this and what you hope to accomplish?
Yeah. I'm really honored to be part of that advisory board for the UN, and in these tricky times with a lot of geopolitics there, which again, I'm not the expert on that, but when it comes to, aspects, especially related to AI, having scientists in the room is something that, I think is very important. I hope I could have an unbiased view and try to provide scientific evidence for any aspect, right? We want to think about how AI impacts globally, like, how do we ensure the benefits of AI reach everybody? How do we democratize access to AI? How do we ensure the unintended consequences and harmful impacts can be controlled? I think these are just the beginning aspects. Of course, the other side, when it comes to weather models, I'm already excited. Like, there is a push to seeing how we can have better weather and climate modeling. So then, or food, like using weather for better agriculture. So all these aspects are also where UN has a lot of dedicated agencies and people on the ground across the world. So I'm looking forward to contributing and being part of this.
Looking at your career and how you, talk and what you work on, it seems like you very much are a person who likes to solve concrete problems. You don't like to philosophize about things, and you also seem, I think, maybe more optimistic than a lot of people in the AI space. You have a very hopeful view of the world. I think it's not necessarily always true. What are the ways that you can uniquely bring that viewpoint to the board versus maybe some,
Thank you. I to me, I think, as I said, I try to be unbiased and as a scientist. And as a scientist, I think that there's a lot of beneficial aspects of AI that are sometimes missed when we think of only the harmful impacts, right? And especially that is with respect to AI for science, because a lot of regulatory frameworks equate AI with language models. And yes, language models can, manipulate people, can have all these kinds of harmful impacts that we should think about controlling. But AI for science is different. So I think this one size fits all is where a lot of problems come up. So we have to be mindful that there is, AI that can change the world with new discoveries, and we should enable people around the world to not only benefit from them, but also be able to do research, have access to AI that they can go innovate and use them in interesting ways.
One question that we have been trying to ask every guest is, if you could pick a bottleneck in your domain that you could magically remove, what would that be and why?
More compute. That's I know that's an easy one, maybe a lazy one, right? Fair. Because, of course, our compute that we have is growing so much more than even a few years ago, thanks to NVIDIA, thanks to others.
Again, there. Yeah.
So no comments on that. But what I mean by that is also like for research, enabling more and more compute, it's very important. I know there are national labs building more supercomputers, hoping that we can have more compute for research. But I think, without that, we cannot experiment, we cannot innovate. I think this is a part that I push a lot, and, I think I cannot emphasize that it's so critical.
If you had a call to action or something that you would like people to do or think about or learn about, what would that be?
Yeah, so, you can go to neural operator libraries, so you can kind of hands-on play with different architectures, recipes, look at use cases, but also think about AI for science as not just language models and agents. Yes, that's one aspect of it, but ultimately, those are still like external wrappers in a way, right? Until we have AI that fully understands the physical world, not just as symbols, but as one that can simulate and design and control based on that, there's a big piece missing. So that's the other aspect that I think the people should really think about AI for the physical world in this way.
Anima, this has been so fascinating. I'm excited check out neural operators myself. I have some ideas in my head already. I really appreciate you taking the time to sit down with us.
Yeah, thank you, Arjit. Thank you, Brandon. I really enjoyed it. We really dug deep into a number of things. So I appreciate you doing that.
Yeah,
thank
thanks.
you.
Thank you.
Great.